Welcome to another deep dive, everyone. Today we'll be slithering back in time to explore the fascinating world of prehistoric snakes.
Yes, a journey millions of years in the making.
Exactly. We've got tons of listener questions and some awesome material to dig into, so
Yeah, it should be a lot of fun.
absolutely. So let's start with the basics. What kind of fossils are we talking about here, and what are we hoping to learn from them?
Well, we're primarily looking at skeletal remains. Skulls, vertebrae, ribs, sometimes even complete skeletons if we're
Oh,
lucky.
wow. Complete skeletons. That's amazing. What can those tell us?
Well, complete skeletons give us that really clear picture of the snake's anatomy, right? Like its size, its shape, and even how it might have moved.
Right. So it's like putting together a giant prehistoric puzzle.
Exactly. And from those pieces, we can start to understand how these ancient snakes lived, how they evolved, and how they fit into the broader ecosystems of their time.
So it's not just about bones. It's about reconstructing entire worlds.
Absolutely. And it's a world that's both familiar and strangely different from the snakes we see today.
Now, you mentioned evolution. So where do we even begin with a story that spans millions of years?
Well, a great starting point is with one of the earliest known snakes, Eophis underwoodi. It's called the dawn snake.
Okay, the dawn snake.
Yeah, it dates back an incredible 167 million years to the Middle Jurassic period.
Wow, 167 million years. That's
Mhm.
hard to even fathom. So where was this dawn snake found?
In England. And its fossils are really helping us understand the very early stages of snake evolution.
So what can Eophis tell us about those early snakes? Did it already have all the classic snake features?
Well, not quite. It's considered a pan snake, which is like a broader category that includes those early snake-like reptiles.
And snake.
Uh,
Interesting. So some had legs, some didn't.
exactly. They were all sort of experimenting with different body plans on their way to becoming the snakes we know today.
So it's like a snapshot of evolution in progress.
Precisely. And as we move through the fossil record, we see snakes experimenting with different lifestyles. For example, take Najarash from Argentina.
Oh.
Yeah, this snake gives us really strong evidence for what we call the burrowing hypothesis of early snake evolution.
Hold on, burrowing snakes. So you're saying snakes might have started out living underground.
That's the idea. You see, Najarash had small but fully formed hind limbs.
Wait, so it had legs?
Yeah, tiny ones,
Ugh.
which suggests it spent a lot of time underground. That burrowing lifestyle likely helped shape their long bodies and eventually led to the loss of limbs altogether.
Wow, that's fascinating. So it's like they found a safe haven underground and gradually adapted to that environment.
Right, and it's an adaptation that we still see in many snake species today.
Really? So some modern snakes still burrow.
Oh yeah, plenty of them. It's a testament to the effectiveness of that ancient strategy.
That's a great connection between those prehistoric snakes and the ones slithering around today.
It is. And then there's Eupatophis discoense, which had these tiny little remnants of legs.
Remnants of legs. So like they weren't really legs anymore,
Not really, they were vestigial structures, leftovers from their ancestors.
like evolutionary baggage.
Haha, you could say that. But those tiny legs are like whispers from the past, giving us clues about their evolutionary history.
Wow, so those tiny legs tell a big story, huh? Okay, so we've got these early snakes experimenting with burrowing still holding on to those tiny legs. What else is out there?
Well, let's dive into the water, shall we?
Snakes in the ocean. I'm intrigued.
Meet Pachyophis woodwardi, one of the first snakes to venture into the ancient seas.
Wow, a swimming snake. So what kind of adaptations did it have for aquatic life?
Well, it had thickened ribs and vertebrae.
Okay, and what does that tell us?
It suggests it had larger lungs, which would have been perfect for diving.
So it could hold its breath for longer.
Exactly. And get this, it didn't swim with the typical serpentine motion we see in modern sea snakes.
Really? How did it swim?
It relied more on powerful tail-driven movements.
So it was less like a snake and more like a swimming lizard.
You could say that. It really challenges our assumptions about how ancient snakes moved and interacted with their environment.
Yeah, that's a fascinating adaptation. So it makes you wonder, were they powerful swimmers, or did they kind of just lurk on the seafloor waiting for prey?
Those are great questions, but unfortunately the fossil record doesn't always give us all the answers. We have to use our imagination and scientific knowledge to fill in the gaps.
Right, so it's like we're piecing together a giant prehistoric puzzle with some pieces still missing.
Exactly. But those missing pieces just make the puzzle even more intriguing, don't you think?
Absolutely. Now I'm ready to hear about some of those more fearsome prehistoric snakes. What can you tell us about Sanajeh indicus? I heard it had a thing for dinosaur eggs.
Ah, yes, Sanajeh, the nest raider.
The nest raider, what does that mean?
Well, this snake had incredibly flexible jaw joints, which is a characteristic of the Matsoidae family.
That's soy day. Got it.
And those flexible joints allowed it to swallow prey much larger than its head, like dinosaur eggs.
So it could basically unhinge its jaw like a modern-day python.
Exactly. And it's this adaptation that made it such a successful predator in those dinosaur-dominated ecosystems.
I can just picture it lurking around those giant nests waiting for the opportunity to strike. So were dinosaur eggs its only source of food?
And while we have evidence of it preying on eggs, we can't rule out other prey items. It's possible it had a more diverse diet.
Makes sense. A snake that can swallow an egg can probably swallow a lot of things.
Yeah.
Which brings us to another giant, Madsoia madagascariensis, right?
Oh, yes. Now we're talking about a true giant.
So how big was this one?
Well, it was comparable in size to a modern-day boa constrictor, maybe even bigger. Its robust vertebrae and powerful muscles would have made it an incredibly strong constrictor.
So it was the king of its domain, ruling the ancient ecosystems of Madagascar. But I know we've got even bigger snakes to talk about, right? What about Pachyophis colossaeus?
Pachyophis was a true sea serpent. It was absolutely massive, potentially longer than a school bus.
Longer than a school bus. Okay, now I'm getting a little scared.
It was perfectly adapted for life in the ocean, with a streamlined body, reduced limbs, and maybe even a fin-like tail.
A snake longer than a school bus swimming through the ocean. That's a mental image I'm not sure I want to dwell on. But I definitely want to hear more about those giant snakes,
Yeah.
especially Gigantophis and, of course, Titanoboa.
Yeah, Pachyophis was definitely impressive. But before we get to Titanoboa, there's another giant we need to talk about, Gigantophis garstini.
Gigantophis. Okay, I'm ready.
Yeah.
How big are we talking?
Well, based on its vertebrae, we think it was somewhere between 30 and 35 feet long.
30 to 35 feet. Wow, that's like longer than a telephone pole.
It was a true monster snake,
Yeah.
a top predator in its environment.
So what did it eat? Anything it wanted to?
Probably. We think it might have hunted early elephants, even crocodile.
A snake eating a crocodile. Now that's a prehistoric showdown I wouldn't want to see.
Mm-hmm.
So this Gigantophis was like the king of its time.
Absolutely. It ruled the swamps and waterways, but eventually it went extinct, paving the way for other giants, like Wonambi neocordotensis.
Nambi. Okay, so this one came after Gigantophis.
Exactly. And it survived in Australia until relatively recently, which means it lived alongside those giant marsupials and reptiles we talked about earlier.
So it was like a more modern giant snake.
You could say that. And its jaw structure was similar to those Matsoidae snakes we mentioned.
Right, the ones with the super flexible jaws.
Exactly. That allowed it to swallow large prey, even though its gape wasn't that big.
So it was a powerful predator, even with those limitations.
Oh, yeah. It could tackle some of the biggest animals around. So, yeah, it was a force to be reckoned with.
It's amazing to think about those ancient ecosystems with all these massive creatures roaming around. But I think it's time we finally talk about the big one. The one we've all been waiting for.
Titanoboa.
Titanoboa ceruginoensis, the heavyweight champion of prehistoric snakes.
That's the one.
So tell me everything. Just how big was this thing?
Get ready for this. Titanoboa was somewhere between 42 and 49 feet long.
42 to 49 feet. Are you serious?
And it weighed over a ton. That's longer than a city bus and heavier than a grand piano.
That's just insane. I can't even wrap my head around a snake that big. What would it have been like to see that thing in person?
Terrifying, to say the least. But you know what's even more interesting than its size?
What's that?
What Titanoboa tells us about the climate back then?
Okay, I'm listening.
It lived during the Paleocene epoch, right after the dinosaurs went extinct, and it was a period of intense global warming.
So you're saying the planet was hotter back then, and that's why Titanoboa got so big?
That's the leading theory. Snakes are ectothermic, which means they rely on external heat to regulate their body temperature. So a warmer climate would allow Titanoboa to grow to those incredible sizes.
Wow, that makes a lot of sense. But how do scientists even figure out the size of a creature that lived millions of years ago? I mean, they didn't find a complete Titanoboa skeleton, did they?
No, of course not. Finding a complete skeleton of any prehistoric creature is incredibly rare, especially one as big as Titanoboa.
So how do they do it?
They study the fossils we do have, the vertebrae, the ribs, and they compare those to the bones of living snakes, using something called comparative anatomy.
Okay, so they basically use those modern snakes as a reference point.
Exactly. And they also use mathematical models to fill in the missing pieces. It's like putting together a giant puzzle.
A puzzle that spans millions of years. That's pretty amazing.
Mm-hmm.
So speaking of puzzles, what did this massive Titanoboa eat?
Well, based on its size and where it lived, we think it probably ate large fish turtles, maybe even crocodiles.
Hold on, a snake eating a crocodile. Come on.
It might sound crazy, but Titanoboa was an apex predator. It was at the top of the food chain.
I guess when you're that big, you can eat pretty much whatever you want. It's incredible how much we can learn from just a few fossilized bones.
It is, and Titanoboa is just one piece of the puzzle when it comes to understanding snake evolution.
It's like a window into the past, allowing us to see how these creatures lived and thrived millions of years ago. But there's so much more to learn, right? It really is. From those little Eophis to the mind-blowing Titanoboa, it's amazing how snakes have made their mark everywhere, from underground to the ocean.
It's that adaptability that makes studying them so fascinating. They really show us how life on Earth has changed and evolved over millions of years.
It's like they're a living record of our planet's history. But I have to ask, why should we even care about these ancient snakes? They're long gone, right?
That's a question a lot of people have, and it's a good one. But you see, these fossils, they're more than just remnants of the past. They teach us about the very principles of evolution adaptation, how everything's connected.
So it's about the big picture, not just memorizing names and dates.
Exactly. Titanoboa, for example, it completely changed how we thought about snake size. It challenged everything we thought we knew.
And don't forget, Wonambi, living alongside humans in Australia, makes you realize it wasn't that long ago, geologically speaking, that giant snakes were still around.
Absolutely. It shows how dynamic our planet is and how life is constantly changing. But there's another important reason to study the past.
Okay, I'm curious.
What's that?
Understanding the past helps us make sense of the present and prepare for the future.
I see what you mean. Like, if we see how those prehistoric snakes handled things like climate change, it could give us clues about how snakes today might adapt.
Precisely. It's all about learning from the past, seeing how life has responded to challenges, and that knowledge can help us protect biodiversity in the face of climate change.
So really, it's about connecting those dots between the past, the present, and the future.
Exactly. By studying those ancient snakes, we gain a deeper appreciation for all life on Earth and how interconnected we all are.
So for our listeners out there, why should they care about prehistoric snakes?
Because it's part of our story. It reminds us that we're all connected to this incredible web of life that stretches back millions of years. And by understanding the past, we can better appreciate the present and navigate the future. It's about sparking that curiosity, that sense of wonder about the natural world. Who knows what other amazing discoveries are waiting to be made?
That's the beauty of paleontology. It's a constant journey of exploration and discovery, always revealing something new about our planet's history.
So keep exploring, keep asking questions, and never lose that sense of wonder. The past is full of incredible stories just waiting to be uncovered. Who knows? Maybe you'll be the one to make the next big discovery. Until then, happy fossil hunting, everyone.